Hi, we're Team 2 working on energy harvesting technology and applications. I'm Brad.
I'm David.
I'm Stu.
I'm Kelly.
So today we're going to talk to you about energy harvesting. There's a couple of projects going on in this class that are using energy harvesting technologies. Team 6 is doing the computer lab in India. So they're taking energy from the sun, storing in batteries, and powering up a computer lab. And that is one application. So we're going to give you an overview of some energy harvesting applications, and we're going to go into more detail of how we're using energy harvesting in our project. So energy harvesting is simply the process of taking energy from an external source, whether it be the sun, the wind, or whatever, and converting it to another source for use in whatever application you so please. So why use energy harvesting? Well, one, a lot of it is renewable sources. So it's something that's freely available in the environment, and it can be used over and over again because it's produced from, say, the sun, something that is going to be around for a while. And it also allows for remote charging in applications. So if we're out in India, we can keep our solar panels out there, and it'll charge up the batteries, and then as they are being used, it can be recharged without having to connect to a central grid. And so some more background is that energy harvesting technologies are still at the point where they're used for low power applications. We are building solar cells and wind turbines at a better rate to compete with a central planning power system, but they're still not there yet in terms of efficiency. So a lot of the applications for energy harvesting are low power, something that you can just charge up your phone or some small handheld device. And so, again, another important thing about this is that it's free and readily available. Once you have the material or the mechanical process to harvest the energy, it's going to be ongoing for the lifespan of the parts of the harvester. So we can further use this harvesting technology to store for later or use it now. In our project specifically, we are going to charge a capacitor and then do that in order to transmit a packet over the course of our network. So we'll get into more detail of that later on, but we can use it also for storing batteries and saving it for later. And again, this allows for a charger to be taken out of the equation because we can harvest it from the environment and save it for later. So Kelly's going to talk about some more ways to harvest energy, give you an overview of a lot of the techniques, and you can see some of them are piezoelectric, pyroelectric, photovoltaic, and then there's also, we can harvest kinetic energy, and then what we'll talk about further is RF energy.
So the first way I want to talk about harvest energy is piezoelectric effect. Some of the teams are familiar with this, using it in their projects. It actually converts mechanical strain into an electric current, electric charge that you can actually use. Some of that mechanical strain is human motion, acoustic noise, vibrations, and pressure. Actual piezo is actually Greek for pressure. It's actually taking the material and the piezo material, crystal or ceramic, and actually squeezing it and pressing it and actually getting an electric current out of it. It produces, like David said, a small amount of power, actually milliwatts, which is helpful for using on small handheld devices. But there are current technologies where you actually have clusters of them, a lot of them. Like in this example, this dance floor, it's actually a squishy floor with springs and has piezoelectric material. And as the people dance, they're actually powering up certain parts of the bar or the nightclub, which is pretty interesting. The second way to harvest energy is actually pyroelectric effect. That's actually converting the changes of temperature into electrical current. So certain pyroelectric materials, when you're heating or cooling them down, their crystalline structure actually changes and causes a polarization, which gives you the power that you need. The pyroelectric effect is very efficient. It's stable up to above 1200 degrees Celsius, so you can use it in a lot of applications, especially power plants. Power plants produce a lot of heat, and actually 2/3 of the heat a power plant produces is actually going to waste. So imagine how much power we could actually get if we could convert all that power, all that heat into usable energy. So I also want to talk a little about other forms of kinetic energy. Piezoelectric is sort of like that, but there's also a lot more types of kinetic energy that we're more familiar with, including wind turbines. Wind turbines we're all familiar with. They're used in clusters, kind of wind farms, where they can actually power up a lot of things and add power to the grid. A few other things that you guys might not be familiar with is ocean wave buoys. This actually has clusters of giant buoys in the ocean that are attached to the ground. And as the wave goes through and moves the buoy, the wave transfers its kinetic energy through the buoy and into the power grid, and we can actually use the power of the water. A couple other cool things is human motion. So there's actually a mask being built or studied upon where we can put the mask on and it has many wind turbines in it. And as we breathe, it's sort of like Bane from Batman. As we breathe, it actually moves the turbines and actually can power up our handheld devices on our body. So if you're running and have your iPod on your arm. So the last one I want to talk about is the photovoltaic effect, which is, as you guys know, is solar power. It converts solar radiation into DC current. It's found everywhere. We're all very familiar with it. I just wanted to just say how abundant it actually is and how important it could be if we perfected it. The sun actually gives off about 122 petawatts to the Earth's surface, which is times 10 to the 15th. And in 2005, the world combined only consumed 13 terawatts of power. So that just shows you if we can perfect it and actually consume all the solar energy, we would be able to have a lot of power.
So the final main source of energy harvesting that we looked into is RF, or radio frequency energy harvesting. It's basically the idea of taking radio frequency signals, capturing them, and then converting them to a DC power source that we can later use. So RF energy is available on a lot of different frequency bands, obviously like the IEEE 802.15.4 or 11.4. That's a specific band, Wi-Fi, MeWe, that all uses specific bands. So RF energy kind of falls between this giant range of bands. A lot of different companies are looking at different specific bands for RF energy in particular. But some examples of some things that can give off this RF energy, cell phones give off a lot of RF energy, radio towers, Wi-Fi routers, laptops, even TV signals, and we'll look into a few other things that give off kind of ambient RF energy a little bit later. Similarly to a lot of other energy harvesting techniques, this gives off a very, very small amount of power. So we have to use it in things like low power sensors or low power microcontrollers like our MSP430 that we use in lab, or other low power appliances that we can kind of convert and also use very, very quickly since it is discharging a capacitor. So it's a very sudden power source. Similarly, this is a very short distance application. So we're talking on a matter of typically 5 to 10, maybe even as much as 30 feet. So usually, room to room size is how RF energy is getting harvested. However, PowerCast, the company that we have bought most of our sensor equipment from that uses this RF technology, has recently discovered and proven that they can do it up to 1.5 miles in an RF energy range. So obviously extending this range is huge when looking at trying to harvesting specific RF energy and capturing all these sources. So this is a particular project, or a particular sensor product that we have. We'll dive into more details in each one of these products later, but here's the RF transmitter that's going to transmit. These antennas hook up into this kind of main evaluation board, which then this sensor board hooks up into that. This feeds back into our central node. So we'll get into more details on all of those. First, why would we want to use RF energy when we have all of those other piezoelectric and pyroelectric, voltaic and photovoltaic, and all these other Mother Nature sources that we don't have to produce? Well, say you want a sensor in a room that needs to not have a battery, not have a charger, and you're going to want to throw it in a corner underneath something. You're not going to have sun. You don't really have a wind turbine in the middle of a room, and it'd be kind of weird to have a water turbine in there as well. So we use RF energy. right? We can put it wherever, and as long as we have a transmitter, or something that can pick up all these ambient RF energy, that we can be able to power this without having it wired. Similarly, RF energy has the ability to go through walls. So we can have sensors in walls or in the ceiling or something that can be continuously getting power as well. So there are kind of breaking into three separate power sources that RF can capture. You have intentional power sources, anticipated ambient sources, and unknown ambient sources. So intentional is kind of like our power cast transmitter. It's going on a specific frequency that is always going to be sending out RF signals, and its only job is to send out RF signals to power our sensors. It's not trying to send signals and send data, just simply a band of RF. Anticipated ambient sources are kind of things that we can expect to be floating around in the air, so to say, that are a little bit too unreliable to try to power up an entire sensor. However, we could probably capture a few of the RF signals to convert into power. Some of those are like your Wi-Fi routers that are always producing RF, or cell phone transmitters. Similarly, we know that there are going to be cell phones around. However, it's not as reliable as an actual transmitter. The third area is this unknown ambient sources. So things that are very sporadic that can kind of sometimes capture RF, but we don't always know the frequency range. The frequency range can be very broad and also very undependable. So things like microwave radio links or mobile radios, more specifically like trucker radios or police radios. You don't always know the frequency band it's going to be in, and you don't always know that there's going to be signals in certain frequency bands that you can be in, and when using RF, you kind of want to hone in on those sensors to produce the most DC voltage possible. So I'm going to dive a little bit into this PowerCast sensor node that we have specifically chosen. So this is the actual chip that we have. Like I said, the antenna plugs into here. That antenna captures that RF signal, which then goes into this power harvester. So this is kind of the meat and potatoes of the actual sensor and RF to DC energy harvesting. It takes all this RF energy, passes it through a lot of capacitors, full wave rectifier to convert it to this DC voltage, and then charges up these capacitors. So these capacitors are going to continuously charge this RF energy until it feels like it has enough. So this is the main difference between that battery and the capacitor, like David talked about, between charging up a battery to be used later in a long period of time, or this capacitor that can easily charge and discharge, so we can get those constant, or not constant, so we can get those signals to go every once in a while. So these capacitors will charge up, which will then give this short power, which in that time of discharging the capacitor, it will run current through the sensors, which will grab all the information needed, run the microcontroller, which does signal processing. It groups together a packet of data, and then sends it through this radio module. So if you're imagining the time to discharge a capacitor, you have to have a very, very powerful microcontroller. The only problem with having a power microcontroller is that it usually requires more power. However, with this RF energy, you have to focus a lot on this low voltage. This 3.3 volts of our system power has to do all of this that we required. So this microcontroller has to have a very fine line of being powerful, but also being very energy efficient. So this is kind of the more idea of how the voltage from the capacitor charges and discharges, and how this power of the sensor goes. So as you can see, it's kind of a flat line of capacitor voltage, and then when it gets more of that RF energy, once again, depending on how far away it is, or depending on the frequency that it's capturing, the efficiency, we see once this capacitor charges up to its Vmax, like I said, this discharging time right here is the time it has to do all of its processing, all of the sensor and everything. So we're talking milliseconds. I mean, this is very, very small, very, very quick time span.
So I'm going to talk about specifically the transmitter we actually have that we're utilizing for our particular sensor network application. It's an intentional source, so this is specifically spitting out a 915 megahertz frequency, center frequency actually within it, that is being utilized for our specific RF signal that's just solely focused on getting that signal to get the conversion into the DC power to power the sensor board and complete the packet and transmit that data. It's a directional antenna, so you want to have this particular transmitter pointed directly towards the location of where the sensors are being placed within the room, and there's kind of a particular angles that which it will transmit at that we have. But ideally, you want to have it kind of placed right in front of it, so that way it can successfully transmit that RF signal to get the DC power that we need. So kind of like what Brad went through a little bit with the actual transmission process in terms of the RF signal to the board, then the data transmission back to our actual receiver. We have our power transmitter, which is sending out that center frequency, which then the antennas that are connected to the evaluation boards would then power the, allow the power harvester chip to actually do the RF signal to DC conversion, which would then charge the capacitor, which would power the sensors, collect the packet information, and then send the packet information back to the receiver, which would then be connected to a computer. You could read that data off of that. So this is specifically the power harvester chip that we have on the board, and this is an efficiency versus actually an input power. And the input power is in decibels per milliwatt, or yeah, milliwatt, which is dBm though. And this specifically is just a low power, absolute power ratio that's being utilized in terms of that getting that full power transmission and getting a good signal strength with a high efficiency output in terms of getting a very good RF signal to DC conversion process. So we have our center frequency up to 915 megahertz, but that kind of fluctuates between about 950 and 850 megahertz at this point. But as you can see, as we approach up into a higher decibel per milliwatt rating, which around 4 is kind of a Bluetooth class, about a distance of around, it's actually 10 meters distance, you can see actually very high efficiency outputs of the chip for getting that RF signal to a DC power output. And you can see they group together very nicely around that 55% efficiency for the signal strength. Next here is actually the packet frequency from, in terms of the distance from the actual source of the signal with that our particular sensors or nodes would be placed. At lower distances, and this is in our feet scale, you can obviously see that packet transmission time takes a lot less than you would actually need, because the closer you are to the transmitter, the quicker it can actually find the signal. RF will, of course, with any signal, it will spread out and it can potentially dissipate over time. So as you can see, as we increase the distance, the time to get packets sent back to the actual receiver, to the computer, is going to take a lot longer. But this has been, if this, can be improved upon, which it is being, looked at right now in the industry, that could greatly affect and help the actual RF energy harvesting applications in the future for us. So with the PowerCast right now, we have it where the particular intentional receiver, or transmitter I should say, that's being utilized is being optimized for that 915 megahertz. That's the actual optimized energy band, that range that works to get the highest efficiency output from the RF signal to the DC output. We can, like Brad mentioned, put these nodes in walls, in floors, where we wouldn't have to worry about pulling apart a wall to get access to these sensors in order to replace the batteries. So just having that RF to go through different materials to actually power is going to be greatly beneficial for applications where you're not going to want to have to pull, destroy property to access things and get things maintained and configured in that regard. And then it's great for low power applications. So you don't need a whole lot of power in order to power the sensors and to get that packet information sent to us. There's also additionally the RFID tags that they use in industry as well too, which are just get that very close proximity. Our MSU IDs, just quick scan, which gives you that very low voltage power just to get that transmission and that data sent quickly and efficiently. Yeah, and power energy harvesting is very known today. You can see this clearly in the solar industry right now. Obviously wind turbines, and then even some of the water applications with the buoys. You can see that it's definitely a growing field. Our dependence on fossil fuels, of course, has been a big topic of discussion for the past 10 to 20 years. And as you can see, we've been pushing to try to go into newer renewable energy sources. So RF is just another one of those upcoming renewable sources that we can create and just utilize because it's so highly abundant in our society today, and we have such a frequency spectrum that's available that can be utilized within this field.
Any questions? Yeah.
So you, I know you guys are using RF power. How do you go about like avoiding obstacles?
What do you mean, avoiding obstacles?
So you said with you get 55% efficiency if you have a direct line to source, correct? Or if you have a clear
Yeah.
view between your receiver.
It's not really a clear view. I think it's more of a distance.
Well, I think I know what you're saying. Yeah, you know, going about obstacles with any RF signal, no matter what, is gonna provide a little bit. So having a clear path is obviously gonna improve the efficiency, but with that 915 megahertz frequency, it usually is very good at kind of cutting through, and also the band that it gives and the antenna, it provides a bigger range of what it can capture. So, like we talked about, going through walls is something RF can do, but obviously if you have 20 feet cement thick walls, we haven't done enough testing to show you what's going to happen, but I can make an assumption that it's probably not going to be as efficient.
As long as it's not conducting to the obstacle.
That's the kind of point of the RF energy is get rid of that obstacle.
Do you see as the limitations of using RF? Obviously.
Definitely the range. The range is a big factor. I mean, we were just testing in the lab, and it's the packet frequency just varied.
It drops if you
Dramatically if you just put them far away. I think it's because we didn't have our transmitter placed correctly, but
which is another weakness. Is
Yeah.
Our transmitter is not sort of pointed in that 120-degree angle. Your ARP nodes are not going to be.
The directionality is not.
Yeah.
Yeah.
And also the knowledge of frequency, especially for the idea. This intentional, I think, is a very good going forward thing. They're using a lot of applications. One really cool one is video game controllers. They're now looking into having those RF power so that the consoles of the video games can actually power up the controller while you're playing video games. But that's the intentional source. When they're also looking into like having cell phones charged, anytime they see an RF signal that's not being used, like Wi-Fi routers just spitting out RF energy that can then charge your cell phone off of that. However, this low power application kind of makes it hard to actually capture enough to make it worth it. Also, trying to get that entire frequency range is a huge limitation.
Very good. I think we have time, so thank you very much.